pure semiconductor is completely useless to us. Okay, due to which only it was criticized a lot that this is completely useless. Why is this useless? Because the density of electron and the density of hole are very less, and since they are formed out of due to the creation, they have pure semiconductor is completely useless to us. Okay, due to which only it was criticized a lot that this is completely useless. Why is this useless? Because the density of electron and the density of hole are very less, and since they are formed out of due to the creation, they have the tendency to recombine. So if they will recombine, everything will be finished over there. So what is very important to know that the number of hole and the number of electron created are very small. Okay, and they recombine so quickly. Okay, the tendency to their recombination is very quick, due to which I can say here in this case that pure semiconductor is completely useless to us. And in the initial days when semiconductor was discovered, okay, people and the scientists started to criticize that you have discussed something which is completely useless, because even if I increase the temperature, even if I pass current through it, it is of no use to us. Okay, and why is it no use to us? So there are various reasons. The first reason is that the electron pair created are created, but they get back so easily. The second thing, the density of electron and the density of hole created are very less. Okay, that's all you need to know for now. With this, we are actually starting the topic of two types of semiconductor. Okay, till now we have discussed this pure semiconductor. Now we are discussing about the doped semiconductor. You remember I said that there are two ways to modify a semiconductor. One is by temperature and the other one is by doping. So doping basically means mixing of impurity. Mixing, okay, or you can say impurity that has been created. So if you mix something over there and if you make it impure, you will find that the tendency of a semiconductor is increased to a lot. So on the basis of doping, I can say my semiconductor is either N type or it is P type. It is either N type or it is P type. Let us take it to center and discuss more about this. Okay, so I am having two kinds of semiconductor, the N type semiconductor and the P type semiconductor. Okay, remember that these are extrinsic, or you can say these are impure semiconductor. What are these? These are my extrinsic, or you can say these are my impure semiconductor. This is something which you are required to know it very carefully, that this is my extrinsic or this is my impure semiconductor. Okay, let us discuss more about this. Okay, before going to the next topic, let me just give you the values over here. You should always remember that the energy gap of three, okay, the energy gap of three elements: silicon, germanium, gallium and arsenic. Okay, so these are some of the elements whose electron band gap energy you are obliged to remember. The first is your silicon. For silicon, the band energy gap is 1.1 electron volt. 1.1 electron volt. For germanium, it's 0.7 electron volt, and for gallium and arsenic, it is 1.4 electron volt. Please remember this, because in when you will be giving your examination, let us say you are giving NEET or your physics, so sorry, NEET or JEE, then in those cases you are not given the band energy gap of these all. Okay, these are really important for you to remember. So please remember that the band gap. Okay, the band gap, or you can say the band energy of silicon is 1.1 electron volt, germanium is 0.7 electron volt, and gallium and arsenic is about 1.4 electron volt. Is that clear? Okay, so let's begin with the various kinds of doped semiconductor. So let us begin discussing about the N-type semiconductor. Okay, let's begin with this. So N-type semiconductor, okay, repeating it, okay, these semiconductors are known as impure semiconductor. N-type semiconductor is having pentavalent impurity. Okay, what is the relation between all this terminology? You will be just knowing in a bit of moment, so please hear it out patiently. That N-type semiconductor is having pentavalent impurity. Any idea what is pentavalent? You have already studied chemistry in a deep and thorough manner, so I can hope that you are knowing about this. Okay, well, pentavalent means the one with the valency of 5. Does the valency of 5 exist there? No, valency 1, 2, 3, 4, only these many exist. So basically pentavalent impurity means, okay, I am talking about those elements having 5 electrons in valence shell. Okay, the one who is having 5 electrons in their valence shell, they are known as pentavalent impurity, and these includes potassium, arsenic, tin. Okay, well, if I give you reference from the periodic table, so pentavalent are the one from group number 15. Okay, from the group number 15 of the periodic table, you can see that these are the ones which are called as pentavalent. Okay, the phosphorus, the arsenic. Okay, so these are the one. Okay, what is most important to know about these all is that you can find from here that all of them are having five electron in their valence shell. Okay, you can just do the electronic configuration and you can find it. I'm not gonna waste the time over there. Okay, here. Okay, so what is the need to talk about other atom? Like I am discussing about the semiconductor, I am having my base semiconductor, let us say silicon. I will be making entire discussion with the help of silicon only. So if I am having silicon, then what is the new use of these all? Hear it out. I have used the word that these are extrinsic semiconductor or these are impure semiconductor. Well, impure because you can see that these are mixed with it. And why this is known as extrinsic? Okay, these are known as extrinsic because the impurity, what is the impurity here? The impurity is this the impurity includes phosphorus, arsenic, Sb here. Okay, all of these are having 5 valence electron. Okay, so these valence electron are basically, they are called as that these are fixed, these are free electron. Okay, these are not the bonded one. Who are the bonded one? The bonded one are the electrons of the semiconductor, which is silicon. Okay, so it is having free electron. Which is having free electron? Say which is having free electron? My doping elements like phosphorus, arsenic, these are having free electrons. Okay, now these free electrons are from the donor ion. Okay, these are from the donor ion. Who is now the donor ion here? Well, here the donor ion is my phosphorus, arsenic and all. Okay, this donor ion will basically give me free electron. These donor ion will give me free electron, and these free electrons will be then used to conduct the electricity. Or okay, you can see that this will be used to produce the current. Now what will happen? Let us say that this is my model. Okay, just a minute. Okay, this is my model, which is something like this, that this is silicon here. Okay, this is silicon here, this is silicon here, this is silicon here, this is silicon, this is silicon, silicon again, silicon again, silicon again. Okay, fine. So these are the silicon, this is a silicon element. In this silicon element, I was already having my bonded electrons over there. Okay, I was having my bonded electrons here. Now if I say that these are my bonded electron, okay, if these are my bonded electron, just hold for a moment. If I say that this is my bonded electron, if these are my bonded electron, you can easily find from here that out of among these bonded electrons, there will be free electrons as well. There will be free electrons as well. And where did this free electrons came from? These free electrons came from my donor ion. These free electrons came from the donor ion. These are my free electron and this is my bonded electron. I hope you are getting it. Okay, I know I may be a bit slow. Okay, I may be teaching you a bit slow, but that is compulsory required for your knowledge. Okay, remember it again that I am having bonded electron and I am having free electron is in my n-type semiconductor. In my n-type semiconductor, I am having my bonded electron and free electron. Okay, where did the free electron came from? Free electron came from the donor ion, which is phosphorus, arsenic. What I have done, I have taken a sample of silicon, I have taken, let's say, a sample of phosphorus. I have mixed both of them. Since I have mixed both of them, this is the entire thing here. Okay, and let us say that any one has been occupied by the phosphorus. Okay, let us say that instead of this, okay, due to doping, due to this impurity, phosphorus occupied a place here. Phosphorus occupied a place here, and phosphorus lost its electron. The phosphorus which was having 5 electron, okay, let us say that this was my phosphorus which was having 5 electrons over here. Okay, it lost an electron. The phosphorus lost an electron. So if I say that this was the electron, this electron is lost here, which has gone here. Okay, and this lost electron is now the one which is carrying over here. I hope you got it. So from here I can say that the number of electron is much greater than the number of hole. In general, if I say that earlier I was having 15 electron which was bonded, therefore I will say that 50 electron plus 50 holes were present here. But due to doping, let us say 10 electrons are present here, present more. Therefore now there are total 60 electron, but the holes are still, which is 50. So I can say that the number of electron is much greater than the number of hole, due to which the current due to electron will be much greater than the current due to hole. Okay, the current due to electron will be much greater than the current due to hole. Is that clear? Is that clear, everyone? Okay, but I can say that the number of donor ion, not the donor atom, because earlier it was atom, but once it has donated the electron, now it is an ion. Okay, this is equal to the number of electron, the number of free electron. Okay, the number of donor ion is equal to the number of free electron. Okay, in this diagram I have drawn it more. Okay, but in actual it is equal to the number of donor ion, because you can easily find from here that since it is a pentavalent impurity means out of 5 electron it is just donating 1, so that it can have a stable equilibrium of 4. Okay, this is having 4 electron which is undergone shading. So yeah, 4 have to remain with it, 4 electron have to remain with it, and the remaining 1 electron will go as free electron. Okay, therefore I can say that here number of electron is much greater than the number of hole, from which you can conclude that the number of electron, okay, the number of electron represents the majority charge. Okay, electrons are the majority charge carrier, okay. And what about the hole? So for hole I can say that number of hole basically represents the minority charge carrier. Now what is this majority and minority here? Well, majority represents that here the electrons are more in number, due to which it will be the one which is carrying the main amount of current. Okay, and minority charge carrier means this is the one which is not responsible at all, like it is not responsible to carry majority amount of the current, but still some amount of current is still carried. Why so? Because if I will connect it across a conductor, electron and hole will be created. You can't stop that. Electron and hole will be created, they will be recombined again, they are created, they are recombined. This will continuously take place. Okay, this will continuously take place. Okay, I hope that is clear. Okay, sounds perfect. So if I ask you the net charge of n-type semiconductor is what? N-type semiconductor is what? Like if I give you a piece of n-type semiconductor, the n-type doped semiconductor, so will it behave, will it be positively charged? Will it be positively charged? Will it be negatively charged? Or will it be neutral? Okay, just think for a moment and answer to this question, that either it will be positively charged, either it will be negatively charged, or it will remain neutral at all. You will find that here the overall doped semiconductor, which is the n-type semiconductor, is overall neutral. Oh my god, how is it neutral? Neither it is positive, okay, but it should remain positively charged. Now, why it should remain positively charged? Because phosphorus plus is present. Then it should also remain negatively charged because free electrons are present. Well, what was earlier? Earlier it was pure semiconductor. Since it was pure semiconductor, number of electron is equal to the number of hole, right? Number of electron was equal to the number of hole. On doping with pentavalent donor, what had happened? The number of donor ion that has been created is equal to the number of free electron, right? So earlier also positive and negative charge was balanced, and now also the positive and the negative charge are balanced. Okay, due to this balancing, you will find that there is no net charge on the semiconductor. The semiconductor remains neutral. I hope that is clear. Is that clear, everyone? Okay, so what we came to know about the n-type semiconductor. In the similar way, I will be discussing about the p-type semiconductor. Well, I guess now p-type semiconductor is something very easy for you. Okay, you can easily make a guess that what is p-type of semiconductor. So my semiconductor is, you can say quadrivalent. Quadrivalent means it is having 4 electrons. If I dope it with one element further, okay, that is the 15th group of the periodic table, that will be known as n-type, that is pentavalent. Well, p-type will be the one which is just behind it. Okay, well, which group is behind that? So that is group number 13. Okay, so I can say that my p-type semiconductor is a trivalent impurity. It is having a trivalent impurity. What does trivalent impurity means? Trivalent impurity means that here it is doped with group number 13 element, which is boron, indium and aluminum. Just have a guess, just have a look from the periodic table: boron, aluminum, gallium, indium. So these are the ones from which you can dope your semiconductor. Okay, so my p-type semiconductor will have trivalent impurity, which will contain boron, indium, aluminum, etc. etc. Can you make a guess that here what will be the one which is less or which is more here? You will find that is trivalent impurity. Let us say I am talking about the boron. So boron will have 3 electrons. Nobody wants to have a 3 electron, because 3 electrons basically means that there is instability over there. So what will happen? One electron from the main core shell, from the main core structure of the silicon will be taken. From silicon, this electron will be taken out and that will be emitted here. So boron is negatively charged, and my crystal and my semiconductor crystal will be positively charged. Okay, why will it be positively charged? Because of that bondation, hole is left behind. hole is left behind and the negative charge is carried here. Okay, hole is left behind and this is carried here. I hope that is clear. So I can guess from here that here in n-type semiconductor we were having free electrons in the crystal, but here we will be having free holes in the crystal. There will be free holes, not just free holes, extra free holes. We are having extra free holes because the electron which was bonded there, that has been now carried to the boron. So how will the crystal look here? Okay, before drawing the crystal, I can easily say that the number of hole is much greater than the number of electron. The number of hole is much greater than the number of electron. But yeah, and since number of hole is much greater, I can say that the current due to hole is much greater than the current due to electron. Okay, therefore I can say that here holes are the majority charge carrier. Holes are the majority charge carrier. Okay, and the electrons are the minority charge carrier. It is very important for you all to focus over here because you can easily identify that all these are sequential. Okay, the first thing, all these are sequential and these are the ones from which MCQs are generally asked. Okay, so if you notice, definitely it's good for you. So holes are the majority charge carrier in which type of semiconductor? P-type semiconductor, and electrons are the minority charge carrier. Okay, still I can say that the net charge over here is 0. Why the net charge is 0? Because in pure semiconductor, number of hole is equal to number of electron, because that was in bonded state. Okay, and now in doped condition, the number of donor ion which is negatively charged here is equal to the number of holes created, the number of extra hole created. Is that clear? Okay, and the holes are a positive charge. So overall I can say that the electron and the negative and the positive charge are balanced. The negative and the positive charge are balanced. Is that clear? Okay, so here earlier my pentavalent atom, my group 15 element was the donor ion. This was the donor ion. Here this can't be called as donor ion, which is a wrong term over here. I can call that this is an acceptor ion. This is an acceptor ion. Is that clear? Okay, I hope you got it, that this is my acceptor ion. So what is the thing I can find from here? Well, I will say that if this is my entire structure of silicon, if this is my entire crystal of silicon, just a minute. Okay, of this crystals of silicon, I will find that any one has been when I have doped it. Okay, when silicon is, let's say, mixed with trivalent element.
It's lack of personal attention. With one-to-one mentoring, every doubt is addressed, every concept is applied, and real improvement begins.